Connecting. Okay. So welcome back. So next we have Koushil as the next speaker. So Koushil is an assistant professor of mechanical engineering at UC Berkeley. He received a PhD degree in electrical engineering and computer science and MS in applied math from the University of Michigan, Ann Arbor in 2011. He was a postdoc at the Grass Lab at UPenn from 2011 to 2013 and an assistant professor from 2013 to 2017 at Carnegie Mellon University. His research interest lies in the intersection of highly dynamic robotics and applied nonlinear control. His work on dynamic legged locomotion on the bipedal robot Mabel was featured on the Discovery Channel, CNN, ESPN, Fox, and CBS. His work on dynamic aerial manipulation was first featured on IEEE Spectrum, New Scientist, and Huffington Post. His work on adaptive sampling with mobile sensor networks was published as a book entitled Adaptive Sampling with Mobile Wireless Sensor Networks. He received the Best Paper Award in Robotics, Science and Systems Conference in 2013 and a Google Faculty Research Award in Robotics in 2015. So his talk will be about safety critical control with model uncertainty, a reinforcement learning approach. So with that, over to you, Koushil.
Hey, thank you, Shishir. Thanks for inviting me. I've had like nice fond memories of visiting IISc, so it's good to be back, although virtually this time. So let me get started. So I want to first thank my collaborators, my funding agencies, and my students who made this work possible. My students do all the hard work, and I steal their credit. All right, so let's start with some fun projects that are happening in my group. So here's a legged system on your left. This is the Cassie Juggle robot. Now, the goal is to combine locomotion and manipulation. On the right, you'll have hovershoes. So these are like segways for each foot. So here's a controller that works on this robot. It can autonomously drive this legged system on wheels. So just a sample of a project in a lab. Here's another example, how you combine locomotion and manipulation. So on the left, you have your Cassie system. You want it to bounce balls using a racket. Now, obviously, this system doesn't have hands. So one thing you can do is you can mount the racket on the head. And while you're balancing on the ground, you try to bounce the ball. Okay, so today's talk, unfortunately, is not on either of these projects. It's in the intersection of safety critical control and reinforcement learning. And just a warning, there's a lot of math ahead, so get ready. I'll try to go through it carefully. So here's an example of a safety critical control for a legged system. So these stepping stones are like your lane markers. So your foot has to land on the stepping stones for your system to be safe and to avoid failure. So just like autonomous cars, you have safety constraints, which are really critical for legged systems. So in today's talk, we'll look at a control approach and we'll explore 3 different axes. So we'll start control Lyapunov functions, which can be used to guarantee stability for nonlinear and hybrid systems, as well as for stabilizing periodic orbits. And we'll explore in the direction of enforcing constraints. So these constraints could be input constraints, force constraints, etc. Then we'll look at control barrier functions for safety critical constraints. And then we'll introduce model uncertainty, and we'll use a data-driven approach using reinforcement learning, first on the CLF and then on the CBF. And then we'll show you some simulation results. All right, so let's get started with CLFs and CLF-QPs. So I'm looking at legged systems. So legged systems can be modeled as a hybrid model. So you have a continuous time nonlinear system, x dot is f of x plus g of x times u. And then you have a discrete reset map. You can also define an output function. And the goal of a controller is to drive this output to 0. And we can do this by looking at the output dynamics. So if I just look at the output dynamics y dot, I can write down this in terms of this Lie derivatives, LFH plus LGH. And the outputs that we pick here, most of them have LGH equal to 0. So y dot is not dependent on u. But if you look at y double dot, so you take the next time derivative of this, it's LF square h plus LG-LFH times u. So this is your output dynamics. You want to drive your output y to 0. So this output has vector relative degree 2. So we'll talk about relative degree later. Now let's look at what an output is for a legged system. So here's an example of a cartoon. So you have this legged system that's falling forward. So the angle theta is increasing. Now the joint trajectories, the desired joint trajectories on the thigh and the knee are some function of this angle theta. Now, as long as you drive y to 0, these constraints are enforced. And if your robot falls forward faster, then your swing leg comes forward to catch itself from falling. So these outputs are building in reflexes into your system. And your control goal is to just drive this output y to 0. So some background. So you have a dynamical nonlinear system. You define these outputs, which are shown at the bottom. You look at the outputs and their time derivatives, y and y dot, and your control goal is to drive them to 0. Now, one controller that can do this really well is your input-output linearizing controller. So all it does is it takes this nonlinear system and converts it into a linear system. So your nonlinear output dynamics are given by this. Y double dot is LF square h plus LG-LFH u. Now, if I design a controller U that basically cancels away all the nonlinearities and replaces it with this linear system, I would get this system. Now, I/O linearizing controllers are notorious for being highly dependent on the model. So we look at how model uncertainty can still be used with I/O controllers. Now, once you have this linear system, I can design my favorite linear controller. And this could be as simple as a PD control. Now, what you get is a closed loop linear system where your eta dot is A times eta. Now, instead of using a PD control, we want to use a slightly more sophisticated control with guarantees on stability through Lyapunov functions. So if you take this closed loop linear system, then we can design a quadratic Lyapunov function. V is eta transpose P eta, where P is chosen by solving the Lyapunov equation. And the goal of a controller is to choose this control input mu such that it satisfies this V dot plus some constant times V is less than or equal to 0. If you can do this, then your outputs and their time derivatives exponentially decay to 0. Now, one way to do this control design is by looking at this expression. When your control input is 0 and the left-hand side is negative, then I can choose my control input to be 0. I don't have to do anything more. But if my left-hand side is positive when my control input is 0, then I can design a control input that makes my left-hand side at least 0. Now, one such controller from earlier work is the min-norm controller. Now, what we discovered is this min-norm controller can be formulated as a quadratic program. So this is the control Lyapunov function-based quadratic program, where you're minimizing the control effort subject to this Lyapunov equation, V dot plus constant times V is less than or equal to 0. Now, once you have a quadratic program, you can enforce other constraints. So you can throw in input constraints, force constraints, and contact constraints, and so on. Now, this comes at a drawback. So these two constraints can now conflict. So you need to relax stability to enforce constraints. Now, you can also implement this optimization online on a robot at 1 kilohertz. So here's an experimental validation, where this experiment was run from over 1,000 kilometers away. This was far before we got hit by the pandemic. Now we have to routinely run experiments remotely. All right, so we looked at stability through control Lyapunov functions and control Lyapunov function-based quadratic program for constraints. Let's look at safety critical constraints. Now, safety critical constraints, we talked about this. For an example, for a legged system is to walk dynamically on stepping stones. Now here the skid does land on the stepping stone, but he fails to account for the water, a thin film of the water on the stepping stone. So the contact constraints are also important. So we'll use control barrier functions for enforcing safety constraints. Now, to understand this, let's revisit control Lyapunov functions. So we have a Lyapunov function V. We want it to be driven to 0. And we do this by choosing a control input U such that it satisfies this constraint. If you can do this, then V is exponentially driven to 0, which basically means the state evolves in the region such that V is in this green region. So it's upper bounded by an exponentially decaying function. Now let's look at an example of a safety constraint. I have a safety constraint. So that's state dependent, possibly time dependent. So I always want to guarantee B is greater than or equal to 0. Now I want to use my control input to guarantee this, but it turns out B is not dependent on U. So one thing we can do is we can look at the time derivative of B. And if the time derivative of B is dependent on U, you can enforce this particular constraint, B dot plus some constant times B is greater than or equal to 0. What this does is it makes sure that B is always above an exponentially decaying function, which basically means your state evolves such that B is in this green region, which then indirectly enforces that B is always greater than or equal to 0. If you look at these two constraints, they're very similar. The only difference is the inequality sign. And these two constraints are also linear in terms of the control input for a control-affine system. So you can formulate this together as a quadratic program that can be solved really fast and online. Now here's an example. Now before we go to the example, there are a couple of drawbacks of this approach. There are 3 drawbacks. So one, B has relative degree 1, which means B dot has to depend on U. Now this is not strictly required. There are other approaches. We can use exponential control barrier functions to do arbitrary high relative degree safety constraints. The second is both V dot and B dot are dependent on your model. If you have an imprecise model of your system, this controller will not work. Now we'll see how to address this later in this talk. The third main thing is we are assuming that this optimization is feasible. So the guarantees of feasibility is something that's still an open problem. All right, so once we enforce CLFs and CBFs, we can apply this to legged systems. So here's an example of a legged robot walking on a terrain of discrete stepping stones. The controller has only one step knowledge of where the next stepping stone is, so it doesn't know the entire terrain. So here we're using one periodic orbit with the control barrier function. Now here's an example where you have a higher dimensional humanoid robot where the step length and the step width changes. Now, if you use multiple periodic orbits with the control barrier function, then you can walk on a whole bunch of terrain. So here's the Atreus robot walking on stepping stones. The controller is provided only one step ahead knowledge of the next stepping stone, and the step length changes randomly. Here's an example where the step length and the step height changes. Okay, so this is looking good, but the main drawback is we need a precise model. So what happens if your model is way off, or if your model changes while you're doing your experiment? So we'll look at an approach using reinforcement learning, first for control Lyapunov functions, and then we'll extend it to control barrier functions. Okay, so here's model uncertainty. So the plant has a true model that we do not know. But what we know is our best guess of the model, which is our nominal model. So a controller has to be designed by the nominal model, but we want to somehow make it work on the true plant, and also want to provide some guarantees on stability and safety. So this is what we had so far. We had an input-output linearizing controller. We threw in a CLF-QP controller on this system. We assumed we knew the model, so the input-output linearizing controller did work. But now if I change my model, if I have uncertainty, and my nominal model is given by x dot as f tilde plus g tilde times u, and I don't know my true model, my IO linearizing controller would be this, with this nominal values of f tilde and g tilde. If I apply this particular IO linearizing controller, then my linear system is no longer linear, it actually becomes nonlinear. So I have delta 1 and delta 2, which are both unknown as well as nonlinear. Now, if f tilde is equal to f and g tilde is equal to g, then both delta 1 and delta 2 become 0. and you recover your initial system. All right, so let's look at the first approach of using reinforcement learning on an IO linearizing controller. So what we have on the left is what we've seen so far. If I use an incorrect model, I get a nonlinear system for my output dynamics with some uncertain terms. So we want to compensate for this uncertainty. So we'll use a slightly different controller. So we take our IO linearizing controller. So we take this plus this. So this first two terms with this inverse is your standard IO linearizing controller. But then we add two additional terms. One of them is linear in terms of the control input. The other one is just a drift term. Now theta are your network weights, and these two terms are what needs to be learned. If I apply this particular input, my output dynamics will then look something like this. So I have y double dot is mu, then I get delta 1 plus beta plus delta 2 plus alpha times mu. Now, as you can guess, our goal is to make sure that beta cancels delta 1 and alpha cancels delta 2. And we create a reward for reinforcement learning. So we take a measured value of y double dot, and we want to make sure that it is equal to mu. So we can recover a linear system, y double dot is equal to mu. So now you can train your network with this particular reward on your dynamical system with your controller in the loop. But we'll also look at the second approach, which uses control Lyapunov functions, because the second approach can then be used for constraints and for safety. So here's control Lyapunov functions. So we had a quadratic program. We wanted to minimize your control effort, subject to the constraint v dot plus some constant times v is less than or equal to 0. Now this v dot depends on my input. So if I expand v dot, so v dot is this Lie derivatives LFV plus LGV, and the model dependence comes out here f and g. Now if I apply my nominal model, which is different from my true model, then v dot would actually have these terms. So I get my nominal v dot, which is LFV plus LGV, where f and g are my nominal models. But then I get this uncertain terms, delta 1 plus delta 2 times mu. I can now create a predictor for v dot. So I define this predictor. It's parameterized by the network weights theta. It has a very similar structure to this first one. So you have this v dot tilde, which is my nominal v dot. Then I add this two additional terms. And as you can see, the goal of beta is to cancel out the effects of delta 1. The goal of alpha is to cancel out the effects of delta 2. Now, once again, I can put in a cost function here. I can look at the measured value of v dot, and then I subtract away my predicted value. So I'm looking at the measured value of this, and I want to minimize this particular cost. And the theta that I get from this, then I can put it in my quadratic program. So my quadratic program is also parameterized by this network weights. Now we tested this out in simulations. So the controller nominal model was a system that looked like this. And we took the mass and the inertias of each and every link in the robot, and we doubled it. So your true system looks something like this. The controller is designed on this nominal plant. Now, once you train on this plant, your controller works. Now, don't worry about these plots. Just take my word, this controller does work pretty well. But we also want to see if this controller with this reinforcement learning works on a model uncertainty that wasn't trained on. So we took another plant, where we took the nominal plant and then added a huge mass on the torso. So we added 72 kilograms of mass, which corresponded to more than twice the weight of the robot. And now this particular uncertainty was not trained on, but this controller with the reinforcement learning still works on this particular thing. Now, just for comparison, this yellow plot is of for an adaptive controller that was really good, but failed for this large uncertainty. So combining reinforcement learning with formal control is pretty good. Now we want to look at, can we also add this to barrier functions? So then we can also address safety critical constraints. All right, so this is just a motivation. So you want to do both model uncertainty as well as safety. Now it turns out we can apply a very similar technique for barrier functions. Now if I apply my IO linearizing controller with the nominal models, then I get B dot, which has these two uncertain nonlinear terms, very similar to what we had for the Lyapunov function. Then we can create a predictor for the barrier function as well. And the goal is to learn this network weights so that beta cancels out the effects of delta 1 and alpha cancels out the effect of delta 2. So we can once again create a cost function which minimizes the measured value of B dot and this predicted value of B dot that we created. Now, once you have this, we can combine it with the Lyapunov function. We can also do this for additional constraints, which I'm not going into here. You can create one reward that captures all of these costs together. And then the theta that comes in then can be applied on the quadratic program. So you have a RL-based CLF, an RL-based CBF, and you can also have RL-based constraints. So you can then solve this quadratic program and then apply the control input from the output of this QP to your system. So just to illustrate this pictorially, so this is what's happening. So we have our plant, x dot equal to f of x plus g of xu. F and g is unknown. Our best case of the plant is f tilde and g tilde. Now from this f tilde and g tilde, we're computing v dot, b dot, and these are the constraints. In addition, we're learning this alpha and beta parameters for the Lyapunov function, for the barrier, and for the constraints from a network using reinforcement learning. Now we're adding these two things, and then we're sending it to the QP. And the QP is enforcing a constraint based on this predicted value of v dot and b dot. The input that you get is then applied to the plant. So the safety critical constraints are computed from this nominal model. You're getting the alpha and beta from the reinforcement learning. You're combining that and then solving a QP. Now here's a simulation result of this controller working on a terrain of stepping stones. So we're working on experimental validation, and we have some tweaks to improve sample efficiency as well. So here's some plots, basically that shows that the foot does land on the stepping stone, and you're also not violating the contact constraints. Okay, to summarize, so we've explored designing controllers along 3 different axes of constraints, model uncertainty, and safety constraints. And we use reinforcement learning to address model uncertainty. So with this, I would like to stop, and I'm happy to take any questions. Thanks everyone for listening. Hopefully the math wasn't too bad.
Okay, yeah, thanks a lot, Koushil, for the excellent talk. So, like I said, if you want to applaud the speaker, please use the button below. So, as you can see, Koushil, everybody is clapping here. Okay, so time for questions. So we have a question, the first question from Meenakshi Sarkar. So the question is this: what happens when we have the lead derivative going to 0 for states inside the safety boundary? A problem that we faced with designing exponential CBS for stochastic systems. This kind of scenario induces numerical instability for the QP.
So the definition of the CBF requires your LGP not to be 0. And depending on the relative degree, you would need a different term to be non-zero. So it's not a valid CBF. Okay.
So in other words, okay, let me add more to that. So if there is a constraint function whose lead derivative has this property, then that has to be modified in such a way that the lead derivative, the LG, does not become 0, right?
So you need to formulate a different safety constraint.
Okay. Okay.
That would be valid. So you could do this. So if you take a quad rotor system, so typically the lead derivative LGB, one of the components goes to 0. But you can redefine a different output.
Okay. Okay, great. So, So Meenakshi again has a second question. In your paper, how do you design the explicit expression for V, B, and zeta for the loss function?
Just pulling up the slide.
Yeah.
So I'm guessing you're talking about this V dot.
So the part where there is zeta term.
Zeta is additional constraints. So these are friction constraints. These are input constraints. The B could be designed using a quadratic Lyapunov function. The B depends on your application. So for stepping stones, we have two different barrier functions to enforce that your foot lands either before the end of the step or after the start of the step. The zeta is a set of constraints for your input and friction and contact constraints.
Yeah, so I believe more details are in the papers that Koushil showed here. So let's move on to the next question. So again, Meenakshi Sarkar, if we follow parallel research on CBF, on high relative degree systems, he proposes to add a state which has a direct connection to the control input to the definition of the barrier function. Okay, so when we tried this for high relative degree systems, okay. Oh, it's an incomplete question. Okay, so I'll leave the first sentence. I'll ask the first sentence itself. So if you follow the parallel research in CBF, he proposes to add a state which has a direct connection to the input to the definition of the barrier function. I did not really understand this question, but Koushil, if you understood, you can answer.
Yeah, so basically your decoupling matrix is singular. So if you look at LGB, if you have multiple inputs, I think one of the component is 0.
Okay, okay.
Or you can change your definition of your barrier function such that your decoupling matrix is non-singular.
Okay, okay.
How do you do that? It's application dependent.
Okay, so we can take this offline. There are also a lot of other questions. So my guess is that these people can send you emails and you can respond, right, Koushil? So with this, end the session. So thanks a lot again, Koushil, for
thanks for having me.
Yeah. So please applaud, audience. Please click the clap button. Okay, great. Yeah. So with this, let's end the session. Thank you.
See you.